Welcome back. This is still Ken, and we're still in lesson 3 of our course on mechanics on motion in 2 or 3 dimensions. In this video, we're going to continue our discussion and we're going to discuss your projectile motions. We begin with our study on projectile motion. So the projectile motion is all about the motion of a projectile. But what's a projectile? A projectile is any body given an initial velocity that then follows a path determined by the effects of gravity and air resistance. So we have here, for example, in the figure, you have a snowboarder launched from a certain angle. Let's say, for example, he is like snowboarding on this in this slope, and he was launched to some angle, and from that angle he was able to move on a path, like say for example a path like this one here, a curved path. Now this curved path here is actually called a trajectory. So this one here, this path that we're talking about here, so this is called a trajectory. Okay, so the trajectory is a curved path followed by the projectile. So again, the projectile is any body given an initial velocity that then follows a path, which we call the trajectory, determined by the effects of gravity and air resistance. Other examples of projectiles are your basketball. When you shoot the ball, okay, you don't shoot the ball on horizontal, you don't shoot the ball on vertical axis, but you shoot the ball with some angle. Or another example of your projectile is your volleyball, right? So when you hit the ball, the volleyball, so it should follow a curved path so that it reaches the opposite side of the net. Or you can also say your tennis ball or your shuttlecock for your badminton. You can think of other examples. Even you can also throw yourself and be a projectile. Okay. So in our study of projectile motion, we begin by neglecting air resistance and the curvature and the rotation of the Earth, and you will see why this is so. So again, we start with an idealized model. So in our idealized model, we represent your projectile as a particle. So instead of looking it as a ball or a another bigger body, we represent your body as just a particle, just a point. Okay, and here in our analysis of your projectile motion, we neglect the effects of air resistance, and later you will see why. And you also neglect the curvature of the Earth. But remember that it is not always the case that we neglect the curvature of the Earth. Like say for example, if we want to fire a missile, let's say from this country towards another country, okay, when you want to fire that missile, we now take into consideration the curvature of the Earth. Okay. Now, as you can see, that the Earth is of course round, and your projectile motion is always confined to a vertical plane, like what we have here. You have your x and y plane only, and this is determined by the direction of the initial velocity. Okay. You have your initial velocity v naught. So your trajectory, which is the path traveled by your projectile, and the space in which your projectile is confined, is determined by your initial velocity. Now, why is it always confined to the vertical plane? Okay, why did we not look into the z-axis? Okay, or the z-axis? Yeah. So it's because gravity can accelerate your particle sideways. It's purely vertical. One thing that can accelerate your particles or your body sideways is your air resistance. But since we already neglect the effects of air resistance, your projectile motion that you're going to take into study here is always confined to vertical plane. The key here is that we can analyze projectiles by treating the x and y coordinates separately. Again, the key here is we can analyze projectiles by treating the x and y components separately. So later in our problem solving, we can solve your projectiles. Like say for example, you want to find the position of your projectile. So we can actually solve it separately by solving the x components first, and then we solve the y components later. So we can use separate equations for the horizontal and vertical components. So if you remember your equations, you can use your x equation separately with your y components. Now, for your projectile, these are the components of your acceleration. Along the x, you have acceleration is equal to 0 here. Now, along the x, your acceleration is equal to 0. That is because you neglect the effects of air resistance. So you have no air resistance. Okay? And along the y, the acceleration is just due to the acceleration due to gravity, which is equal to negative g. And take note here that both your acceleration along the x and y are constant. So that means we can use your 4 equations of motion for constant acceleration. So we can use your equations for constant acceleration. Okay. So again, the key for our analysis of projectile motion is that we can separate the x and y components. So we can solve the problem separately or we can just solve it first using your x equations, and then later we use your y equations. And why is that so? Okay, this figure here, it shows why we can actually do it. So we have here a red ball, which is just dropped vertically, and you have a yellow ball, which is fired from the horizontal. Okay, and both are affected by the acceleration due to gravity. The red ball is dropped at the same time the yellow ball is fired horizontally, so they were set into motion at the same instant. And the white lines, or the strobe marks, are equal time intervals. And as you can see, at equal time intervals, your red ball and then your yellow ball actually accelerates at almost the same instant. Okay, because here the only force or the only acceleration that acts on your red ball and then your yellow ball is the acceleration due to gravity. That is why, as you can see, if you compare the vertical distance between the next point or the next second, your yellow ball and then your red ball has just the same, almost the same vertical distance from its previous position. We can analyze projectile motion as horizontal motion with constant velocity and vertical motion with constant acceleration. Okay, so if you try to look at here, okay, your yellow ball, which is actually a projectile, if you're going to look at its vertical motion, okay, here you have your horizontal motion, and here you have your vertical motion for your projectile. So the vertical motion of your projectile is actually just similar to the motion of your red ball here. Okay, and that is the reason why we can analyze the projectile as horizontal motion with constant velocity and vertical motion with constant acceleration. That is, you have your ax is equal to 0 and then your ay is equal to your negative g. Okay, so let us start analyzing the projectile motion. Consider, for example, here a soccer ball which you kick at some angle alpha naught. Okay, you have again here a soccer ball, and we give your soccer ball an initial kick at an angle of alpha naught, and we give your soccer ball an initial velocity v naught. Okay. Now, um, theoretically, neglecting the effects of your resistance and curvature of the Earth, your soccer ball will follow this trajectory here. Okay, given your initial velocity v naught. But let us just take first this initial velocity here. So as you can see, your initial velocity actually has, we can resolve this one, this vector here, we can resolve this one into the x component. So you have your v naught x, and we can also resolve this one into the y component, or you have your v naught y with respect to this initial angle alpha naught here. And from our previous lessons, your v naught x is just equal to your v naught cosine alpha naught, as this is your adjacent side, and your v naught y is equal to your v naught sine alpha, as this is your opposite side. So this is your x and y components of your initial velocity that you have given to your soccer ball. Okay, so I've stated earlier that since your acceleration for your projectile, so your ax equals 0 and then your ay is equal to negative g, are both constant, we can use your four equations of motion to describe our projectile motion. But for this case, let me just take your equation 1 and equation 2. And we have already stated earlier that we can analyze separately your projectile, separately using your x component and then your vertical component. But for a special case, I just like you to take into consideration equations 1 and equation 2. But of course, later, if you want to use equations 3 and 4, you can do so. But I just like you to focus on equation 1 and equation 2, because your equation 1 gives you the velocity, and then your equation 2 it gives you the position. Okay. So again, we have your ax is equal to 0, and then your ay is equal to your negative g. So that means here, if ax is 0, this one goes to 0, this one goes to 0, and then if your ay is negative g, so we just have your negative g and then your 1/2 negative g. So your equations here becomes, for your equation 1, okay, you have your vx is equal to your v naught x, okay, and your vy is v naught y minus gt. But you already have your terms for your v naught x and then your v naught y. So you have here your v naught x and you have here your v naught y. So your equation 1 for your x, you have your vx is equal to your v naught x. Your v naught x is equal to v naught cosine alpha naught. And then your vy, you have your vy is equal to, your v naught y is equal to v naught sine alpha naught, and then minus gt. Okay, so it's the purpose of this equation here. Okay, so the first equation can be used to find for the velocity of your projectile at any given time t after you kick the ball, given the initial velocity v naught. Like say for example, we want to find for the velocity at this point here. We want to find b at this point here. So to find the velocity at this point here, we can use this equation here, equation 1. And as you can see, you have here your velocity. Okay, so your velocity of course has x and y components. You have your vx here, and then you have here your vy. Okay, so, and as you can see, interestingly, your vx is always equal to v naught cosine alpha naught. So what you can deduce from here is that your um, velocity x, your velocity along the x component is always constant. It does not change. And the reason for this is because we have no air resistance. Otherwise, if there was air resistance, you would observe in reality that uh, your projectile will move more slowly. Later, you will see in a simulation the effects of the air resistance to your projectile. Your Vy, on the other hand, is just equal to your V naught sine alpha minus your Gt. And at any given time t, if it reaches your projectile here at time t, we can use your equations here. Okay? Now let us look into your equation 2. So for your x, you have your x minus x naught. You have your v naught xt. So this is your x minus x naught is equal to, you have v naught cosine alpha naught times t. Okay. Okay. And for your y, you have your y minus y naught is equal to b naught yt minus gt, or minus 1/2. Sorry. This is minus 1/2 gt squared. So your y minus y naught is equal to v naught sine alpha naught times t minus 1/2 gt squared. Okay, so what's the purpose of this equation here, equation 2? So we can use equation 2 to find for the position of your vector at any given time t. Like say for example, I want to look at the position of your vector here. Let's say I want to find for your vector r. So of course your vector r has, you have your x component, and then it also has your y component. And we can use the equations here, okay, this one and then this one, to find for the position of your vector at any given time t. The special case here is that if we begin here at the origin, at this point here, only the special case, again, this is just the special case. The special case is that your x naught and then your y naught is equal to 0. Again, this is just the special case because it is not always the case that we start with the origin. So we have here a projectile motion diagram showing you the various components in your projectile motion trajectory. And we begin with your initial velocity v naught for your projectile. So your initial velocity v naught is given at some angle alpha naught. So it has a v naught x component, and then it has v naught y component. So at later time t, at any time t, this is what your projectile will follow. So this is the trajectory of your projectile. So let's say for example at point 1, this is now, it has now a velocity v1. Okay, and at point 2, which is interestingly at the top of the trajectory, which is usually called the maximum height reached by your projectile. Interestingly, your y component of your velocity vanishes. So as you can observe, if you try to imagine your projectile, it goes up. But while it goes up, its velocity drops, right, until it stops. Okay, its velocity drops, it moves upward, it goes down. Its velocity goes down until it reaches the maximum height, and then once it reaches the maximum height, it then again moves with a faster velocity downwards, so it accelerates downwards. Okay, so at this point here at the maximum height, your y component of your velocity is 0. Why? Because it has already reached the maximum height, so it does not anymore go more higher. Okay, but it still has its x component. Okay, its velocity along the x, because again it has ax is equal to 0, so it has a constant velocity along the x-axis. Now once it goes down from your maximum height, it then accelerates, okay, downwards. Okay, this time the y component is now downwards because your velocity now goes downwards, and it still has the same x component of the velocity until it reaches to 0. So earlier we stated that the key is you can separate your x and y components in the analysis of your projectile. So this is it. So horizontally, the projectile is in constant velocity motion. Okay, its horizontal acceleration is 0, so it moves equal x distances in equal time intervals. You have this one here. So here, this is what you have referred to earlier as your Vx is equal to your V naught x, or you just have your V naught cosine alpha naught. And this is always constant because there is no acceleration along the x component. On the y-axis, you have this one here. It's just like a freely falling body, right? It goes upward and then it suddenly stops at the maximum height and then it goes downwards again. So vertically, the projectile is in constant acceleration motion in response to Earth's gravitational pull. Thus, its vertical velocity changes by equal amounts during equal time intervals. Okay? So we have here an example or a simulation of your projectile motion. So for this case, we have a missile and we give your missile initial velocity of 80 meters per second. And we project this one at an angle of 70 degrees. Now, later you will see some lines, vector lines. So the green lines represent your velocity vectors, and then your yellow lines represents your acceleration vector. You will see here how your velocity and then your acceleration vector changes with time. So let's play the simulation. So as you can see here, the green line, which is the one that is upward, okay? So it starts with a very long line and then when it goes upwards, okay, observe it again, and it goes upwards, it shortens, right? The green vertical line. So let's replay it again. So this one here, this is your velocity along the y, and as you can see, at the maximum height, it stops and then it goes downwards again, okay? Okay, but the horizontal green line remains constant. That is your velocity along the x. It is constant. What is another constant here is your acceleration vector, represented by this yellow line here. Okay, so the only thing that changes is your velocity vector component along the y, and that is because it is acted by your acceleration due to gravity on the vertical axis. Okay, so let's replay it one more time. So that is what happens with your velocity and acceleration vectors in your projectile. So what are the effects of air resistance? If we're going to add air resistance to your model, calculations become more complicated. And if you have your air resistance, the acceleration will not be any more constant. That is, your acceleration along the x will not be any more constant. And the effects can be very large. Like say, for example, it might not reach the maximum height that is reached when there is no air resistance, and the range will also decrease. We say the range, that is how far your projectile is from the original position. And the trajectory is no longer a parabola. Okay, like say for example with this one here, this is the baseball trajectory. The pink trajectory is with no air resistance, and the blue trajectory is with air resistance. So as you can see, it has a shorter range. It also has a shorter maximum height. Okay, and these are the effects of air resistance. Now let us try to view the scenes, the simulation, this time with air resistance. Okay, so let's play this one here with air resistance. But let us review first the simulation without air resistance. So this is again the trajectory of your projectile without air resistance. Okay, and if we put an air resistance with a drag coefficient of 0.47, this is what happens with your projectile. It has a shorter maximum height and a shorter range. So we have talked about the range and the maximum height of a projectile. So in analyzing projectile motion, three characteristics are actually of special interest. So we have already discussed, or we have already talked about the range. That is the horizontal distance of the projectile. So as seen here, the range is measured from the origin towards the farthest point that the projectile has reached. So this is the range here. Another characteristic of the projectile of special interest is the maximum height of the projectile reaches, which we call h. So this one here. And we've already stated that at the maximum height, your velocity along the y component is 0. Okay? And the last one is the total time the projectile spends in the air. So that is the total time the projectile uses up in covering this trajectory here. So let us find the equations which we can use to find the range and the maximum height of your projectile. Let us solve first your maximum height. Okay? How do you find the maximum height of your projectile? H. Again, at the highest point here, you have your Vy is equal to 0. And let us call the time the projectile reaches this point here as P1. Okay? Let's call that time P1. From your first equation, of your equation of motion for constant acceleration, we have your Vy is equal to your V naught y minus gt. But at the highest point again, the vertical velocity is 0. So this one is just 0 here. So we can rewrite your equation such that you have your, this is 0 is equal to V naught y minus gt, or you have your V naught y is equal to gt. And again, we have called that one as your the time to reach the maximum height T1. So let's put some subscript here. And we can use this equation to find the time to reach that maximum height. So your T1, that is equal to V naught y over g. Okay? Now, if, say for example, we begin at y naught is equal to 0, and again, we want to find the maximum height, that is your y at h, okay? From your second equation, we have your y is equal to y naught plus b naught yt minus 1 half gt squared. So this is just 0 here. So we have y, this y equals b naught y t minus 1 half gt squared. And this y here is just your h that we are referring to. But here, your v naught y, which is this one here, this is your v naught y. Okay, your v naught y is just equal to your v naught sine theta naught. Okay, let's just call it your theta naught. Okay, and we use this one to this equation here. So we have your, and by the way, the time here that we're referring to is your time 1. We have here also your time 1. That is the time that your projectile reaches the maximum height. So your equation becomes, you have h is equal to v naught y, and then your t1 is equal to v naught y over g minus 1 half g v naught y over g squared. So this is squared here. Okay. Using your v naught y is equal to v naught sine theta naught term, so your equation h becomes, you have your v naught sine theta naught. Okay, so you have v naught sine theta naught over g. Okay, and this is minus 1 half g. You have v naught sine theta naught over g and squared. So simplifying, you have v naught squared sine squared theta naught over g minus 1 half g, okay, again, minus 1 half g. This is v naught squared sine squared theta naught over g squared. And the squared here can just be cancelled. So you have v naught squared sine squared theta naught over g minus 1 half v naught squared sine squared theta naught over g. And as you can see, this one and this one are just actually the same terms. Okay, we can say that this is, let's say this is x, or let's use another term. Let's say this is k, and then this is also k, because they are just the same terms. You have your v naught squared sine squared theta naught over g. So you have k minus 1 half k. So your maximum height h is just equal to v naught squared sine squared theta naught over 2g. That is, you have 1 half v naught squared sine squared theta naught over g. So you have k here minus 1 half k, so you have 1 half k, or you have your h is equal to v naught squared sine squared theta naught over 2g. And this is our equation to find for the maximum height of your projectile. But again, This formula here can only be used when we start at the origin, which is at x equals 0, and then your y naught is at your y naught is equal to 0. So we have already found a term which we can use to find the maximum height of a projectile, which is, you have derived earlier, you have your maximum height h here, which is equal to b naught squared sine squared theta naught over 2g. And again, we can only use this equation for the special case wherein we have your y naught is equal to 0 and then your x naught is equal to 0. Or when we consider that your projectile started from the origin. Next, how do you find for the range of your projectile? Okay. For the range of your projectile, let us go back to here, at this point here, at the maximum height. Okay. At the maximum height here, we have your time t1 to reach the maximum height. So if this is t1, and this is just 1/2 of the range, that means that at this point here, the time to reach the maximum range, or the farthest point for your projectile is equal to twice of t1. And let's call this one as your t2. So your time 2 is equal to twice of your t1. Okay, so this is equal to your 2, and then you have your t1 is equal to v naught y over g. So this is your t2 here. Okay, and from your equations of motion with constant acceleration, you have your second equation along the x. We have x minus x naught. This is equal to v naught xt. And if we start at the origin, this one here is 0. So we just have your x is equal to v naught xt. And here, your v naught x is equal to v naught cosine theta naught. Okay, and the time that you're referring to here is your time t2, and you're actually solving for the range here r. Okay, so your range r, which is equal to your x, is equal to v naught x t2. Okay, so this is equal to your v naught. Let me rewrite this one. So this is v naught x t2. So you have v naught cosine theta naught, and then times t2. So your t2 is 2 v naught y. So your v naught y earlier is equal to v naught sine theta naught. So this is over g. Okay, this is your x here. Now, we actually have this trigonometric identity. Okay, when you see 2 sine theta cosine theta, the trigonometric identity for this one is equal to sine to theta. And we have here a cosine term and a sine term. Okay, so your x here is equal to 2. You have your 2 v naught squared sine theta cosine theta naught, okay, over g, and applying your identity, you have your x is equal to v naught squared sine 2 theta naught over g, and this is your formula for your range. And again, this is just, or this equation can only be used for the special case wherein we start at the origin. Otherwise, if your projectile does not start on the origin, we need to solve the equation with your x naught term here. Okay.